What's oh.
It's gonna be 2023 soon. That's just
It does happen.
like on my face. This is such a gross number. It's months. Please don't make me that.
Yeah. Trying to do a thing. I forgot what I was saying. I have the department of nutrition. Is that what you said? That's maybe the funniest thing I've ever heard. I was trying to remember what I was doing, and I just. Oh, I know. Okay, there we go. There we go. Chat. Cool. What's that? Something like that. I mean,
Yeah.
because well, technically, like the way because we started. Well, I think we're actually because the first week of school was week 0, right? So then we had like what? Sure.
I counted it out.
Okay, I believe you. Cool. Week 6. We got 4 weeks left in this month. Like a week in December, then finals. Welcome, Alex. There are the attendance from. That's what I was trying to do. Is trying to find it. You grab the attendance when you have a second. Is that smart? Okay. Oh, I should do one thing. Let me see one thing real quick here. Come on in to Co-16B. Check one thing real quick.
The ones which was like
Can't they do the thing I want to do?
It's in her but now we're moving into the exam.
So just a reminder to everyone, next quarter, winter quarter, there will be a 16C workshop. You don't need to register for it. You'll just request to be added to Canvas for it, like you might have done for this class. You can do that whenever. It's going to be Monday, Wednesday, Friday from 10 to 11. So just you obviously if you can't keep that time free because you have another class, you're still welcome to be added. You can watch the videos later. You can also watch the videos later if you're not added, right? Like I post all the stuff on YouTube. You can totally find it there as well. So, but yes, try to keep that time free if you want to come in person or attend virtually live. Yeah. All right. Let's see, where's my stuff? Get all my stuff for myself. So good job. Second here. I mean, over there. Did I not do the thing I thought I did? No, I said a thing and I might have totally spaced it. One moment, please. Okay, that's cool. All right, that's smooth. That's grab that again. And look at that. Okay, sorry, one second. Grab my examples. So grab my one. Okay, so I guess I'll throw it to you all first. Are there any pressing questions about the homework that's coming up that's due on whatever day it's not on section 6.1? Are there any pressing section 6.1 questions? Yeah. Sure. Yes, something similar to 9. I don't want to, so yes. So let's look at something similar to 9. Okay, so something to be aware of about this assignment is not every problem is a substitution. Right, so that's something I want you to kind of be thinking of very generally. I know the section says section 6.1 substitution, right? But in general, if someone gives you an integration problem, they're usually not going to tell you what method to use. Homework is kind of atypical in that way because usually you're in a particular section of the book. But in general, someone's gonna be like, here's an integration problem, you got to integrate it. You might need to use substitution, but in this case, I think we just need to simplify. Oh, I'm looking at the wrong problem. Okay. Well, let's look at the problem I was looking at first, just to point out, just so the thing I was saying wasn't total crap. I was looking at problem 8, which is the integral of 5x plus 6 root x over x, or something like that. And I would just mention, here is a problem where you don't need substitution. You can just simplify and say, oh, that's going to be the integral of 5x divided by x plus 6x to the 1/2 divided by x. And then if I simplify each of those, that's the integral of 5 plus 6x to the negative 1/2. And then we integrate that and we get 5x plus 6x to the positive 1/2 divided by 1/2 plus c, which is 5x plus 12 x to the 1/2 plus c. So yeah, sometimes we don't do the thing that we're looking for, but let's look at what we were actually being asked about, something like the following. Ooh, I can make it worse. Yeah, I can make it worse. I can make it more interesting. How about that? Let's say we have the integral of, yeah, let's say x cubed over the square root of x minus 2. Okay. So with these problems, again, so far, we still really only kind of have, you can either simplify the thing or you can do a u-sub. We're about to finally, next section, today, we will probably talk about today, talk about integration by parts, which is a whole other way of integrating things that we use sometimes. So I look at this and I kind of go down my list. Can I simplify it? No. Can I do a u-sub? I can always try. So we're going to try letting u equal, you could probably get away with either picking x minus 2 or the square root of x minus 2. My word of advice would be to pick the simpler thing first. And if that doesn't work out, then try the more complicated thing. So I'm going to try picking u equal to x minus 2. I'm curious, probably with the other, it would be terrible. So then our du is equal to dx, which is kind of a great situation because if du is equal to dx, changing it all to being in terms of x is pretty straightforward. So changing everything to be in terms of, to be in terms of u, apologies. I'm going to rewrite this and I'm just going to start changing always this first. You always want to deal with that first. Everything else is secondary to that. So dx becomes du. And then we start looking at the rest of it. Square root of x minus 2, well, be quiet. Trig substitution? What? Okay, that's why is my watch telling me trig substitution? So that's going to be the square root of u. And you can either write the x cubed or you can do this back sub right now. Let's go ahead and write the x cubed so that we can kind of be like, okay, well, I did all I could with my u substitution. I still have some x's left over. If that's the case, you either have to do something else or try back substitution. We should try back substitution first because that's what we're going for. But sometimes back substitution won't get you there either. So here now I've got this leftover x. So I take what my u is equal to, and I solve for x. So u plus 2 is equal to x. And that's what's going to go in for our x cubed. So we're going to rewrite this as the integral of u plus 2 quantity cubed divided by u to the 1/2. The rest of this is an exploration in algebra. We have to multiply out this stuff here. U plus 2. Oh, here's something worthwhile. You probably may, I don't know, you maybe seen this before, but if you haven't, it's good to see. So if you're trying, we'll come back to that in just a second. If you're trying to multiply out like something like, I don't know, like a plus b cubed, there's a relatively well-known pattern for this. It's equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. But it's actually coming from somewhere that I think you should all be aware of, because it's really useful if you ever have to multiply out something with a higher power. So there's this thing called Pascal's triangle, where you take some ones and you use some ones, and then you start getting the middle terms by adding those things together. So 1 plus 1 is 2. The next row is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1. And then we get 1, 4, 6, 4, 1, and so on and so on and so on. And each of these rows gives you the coefficients of something like this. So 1 you could think of as a plus b to the 0th. 1, 1 is really your a plus b to the first, which is 1a plus 1b. 1, 2, 1, a plus b squared is 1a squared plus 2ab plus 1b squared. A plus b cubed is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And a plus b to the 4th would in fact be 1a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4th. It's a cool pattern, and it keeps going forever and ever and ever. There's lots of really cool things in Pascal's triangle. I'll remind you all of this later on when we do 16C together and we start talking about probability stuff at the end. There's this thing called the choose function, which is in there as well. So it's kind of neat. Anyway, not the point. The point is that we can easily figure out what u plus 2 cubed is by thinking of u as our a and 2 as our b and writing it as u cubed plus 3 times u squared times 2 plus 3 times u times 2 squared plus 2 cubed, or simplified u cubed plus 6u squared plus 12u plus 8. So that's the point of using it here. It makes it easier to multiply these things out without actually having to like do u plus 2 times u plus 2 times u plus 2 and do a bunch of foiling. So Pascal's triangle, pretty nice. Back to this. So this is going to be the integral of u cubed plus 6u squared plus 12u plus 8 divided by u to the 1/2. And then we have to divide each thing by u to the 1/2, which is really just going to decrease each power by 1/2. So instead of u to the 3rd, you're going to have u to the 5/2. Instead of 6u squared over u to the 1/2, you're going to have 6u to the 3/2, 12u to the 1/2, and 8u to the negative 1/2. They do get kind of ugly, right? Like these problems, there's always a lot of algebra going on. Then we're going to just integrate. So we're going to increase each power by 1. So you're going to u, not 8, to the 7/2 times 2/7 plus u to the 3/2 plus 1 is 5/2. And then we get 6 times 2/5, which is, I'll just write 6 times 2/5. And then I'm going to get 12 times u to the 3/2 times 2/3. And then 8 times u to the 1/2 times 2. Right, instead of dividing by the new power, I'm just multiplying by the reciprocal, but I'm not actually writing it down, I'm just doing it. Finally, let's do one more thing. Plug back in that u is equal to x minus 2. So our final answer here is kind of gross. 2/7 times x minus 2 to the 7/2 plus 12/5 times x minus 2 to the 5/2 plus 12 times 2/3 is 8 times x minus 2 to the 3/2 plus 8 times 2 is 16 times x minus 2 to the 1/2 plus c. Don't forget the plus c. Won't turn out right. I'm going to go from the plus c. So back substitution. It's a little messy sometimes, but sometimes that's all we've got. Good problem. That one's a little more complicated than problem 9, because problem 9, I think, just has a square on top instead of a cube, but same idea. Also in problem 9, I would certainly factor out whatever that coefficient, like if for example, this had been a 7x cubed, my first step would be to bring that 7 out in front. And then you could multiply the whole thing by 7 if you really wanted to. And I would just do that, right? If I had to multiply by 7, I would really just throw a 7 on the whole thing at the end. Okay. Other pressing homework style questions for this particular homework assignment before we get into the next fun stuff. I do also have, I'll be in drop-in right after this. So if you have other questions that you want to come ask me in drop-in, totally cool.
Question 11.
Yeah. So question 11. So let's look. I'll look at something similar-ish to question 11. Maybe can I keep things in order? No, I cannot. It's clearly a failing of mine. All right. So let's look at something. I'm going to switch it up a little bit. Ooh, it's definite. Nice. Let's do the integral from pi over 2 to pi of the 4 times e to the 6 sine of x times cosine of x dx. And hopefully this won't turn out to be silly, but we'll see. I might have made up numbers that are weird. Who knows? All right. So is there a good candidate for a u? Well, first of all, I cannot integrate this straightforwardly. Is there a good candidate for u? I would say 6 sine of x. Now I will show you all later. There's actually 2 plausible candidates for u here. But yeah, I'm going to go with what you said because that's what I would have chosen too. I'm going to go with u equal to 6 sine of x. And I should make sure I can see things. Yeah. So u equals 6 sine of x. And then our du, our derivative, is just 6 cosine of x dx. And again, we're picking 6 sine of x, not so much because it's derivative of cosine, but more because it's stuck inside the exponent. All right, and then I guess we need to, so I really don't love doing it the way your teacher does it, but fine. Du over 6 cosine of x is equal to dx, right? That's still the way your teacher is doing it. Okay. I'll just point out, just so you guys can know a better way of doing it. It's not better, it's better. What I would do personally is instead of doing this crap, that's fine. I would do this. Du divided by 6 equals cosine x times dx. And then be like, oh, boom. There's cosine x times dx. So that's du over 6. That's what I would prefer to do personally. It comes out the same. Sometimes this is doing this way is better though, because, well, we don't want to get into it right now, but it is sometimes better. Anyway, doing it the way your teacher does it. We have the integral of 4. Actually, I should deal with the dx first. So dx becomes du over 6 cosine x. Then you've still got your e to the u, and you've got your cosine x. And here, unlike the previous problem, the x's cancel out, right? Cosine x, we can totally just, cosine x divided by cosine x is gone. Great. So this means we don't have to do a back substitution, which is excellent. So I'm going to write this as the integral of 4 times e to the u du. Now you might notice I haven't written the limits of integration in the last 2 parts. Oh yeah, and hey, thank you, and the 6. Good call. So you have a choice, and I would almost always encourage you to make the choice of changing your limits of integration. You're going to have to do the work at some point anyway. You're not going to avoid it by not doing it right now. So I would encourage everyone to say, well, okay, if x is pi over 2, then u is going to equal 6 times sine of pi over 2. Which is something you're expected to be able to know. Sine of pi over 2 is 1. 6 times 1 is 6. If you don't remember the sine of pi over 2 is 1, you can use a little unit circle. Be like, okay, here's the angle pi over 2. And that circle is a radius of 1. That point is 0, 1, and sine is the y coordinate, which is 1. And then over here at pi, what's the coordinate there? Right, I've gone 1 to the left. So over there at pi, sine of pi is 0. So x equals pi. U is going to equal 6 times sine of pi, which is 6 times 0, which is 0. Now be careful here. My new limits of integration are not from 0 to 6. They're from 6 to 0. Because we have to put the one that was pi over 2 now becomes 6, which was the bottom one, and the one that was pi becomes 0. So we're going to write this like this. And if you don't like them being out of order, that's totally fine. You can change the order by changing the sign. So if you wanted to, although I don't think you need to, you can write this as negative 2/3 integral from 0 to 6 of e to the u du. Not necessary at all. In fact, I don't think I really want to do that. So I'm not, so although we could do that, I'm going to leave it like this and just integrate. So leaving it like this, we're going to get 2/3 times the integral of e to the u is e to the u. I do want to be extra careful or extra explicit about this. Make sure that you are doing the antiderivative. I've seen a lot of people get to this point and just want to plug in 0 and 6. I know for e to the u, it's the same as the antiderivative, but make sure you're actually anti-differentiating your function before you then plug in your limits of integration. That's the whole point of the symbol, is that that's what it's telling us to do. And then we have limits of integration from 0 to 6. And then since we changed our limits of integration, we just get to plug them in. We don't have to do this whole changing back to x and then plugging in what x was. So I'm going to plug in, I'm going to get 2/3 times e to the 0 minus 2/3 times e to the 6, which is something grossly negative. That's fine. That's 2/3 times 1 minus a really big number. That's okay. No one said it had to be positive. It's totally fine to get a negative answer. Unless you know it should be positive, then that's a problem. I will mention here that you could have done this the other way, right? Instead, if you didn't want to have changed your limits of integration, you could have said, I don't want to change them, so I'm going to be like, okay, I was going to have 4/6 integral of e to the u equals 2/3 e to the u, and then we're going to from I don't know what, and then that's going to be 2/3 e to the 6 sine of x from x equals pi over 2 to x equals pi. But I think you might be able to see that this is going to result in the same work, right? We're still going to have to plug in pi over 2 for x, and we're going to get the same result. We're going to get 2/3 times e to the 6 sine of pi minus e to the 6 sine of pi over 2, which is once again e to the 0 minus e to the 6. Same answer. It's fine to do it this way. It just is annoying because then you have to be like, well, I didn't find u's, but I can't just say it's pi over 2 to pi. Typically people will do something like say it's x equals pi over 2 to x equals pi. And then it's x equals pi over 2 to x equals pi. And then it's pi over 2 to pi because it's x. I don't like doing it. It's annoying, but if you want to do it that way, it is a valid way of doing it. It's just less nice. The other thing I wanted to mention is you totally could have done this one with a different u-sub, which is interesting. So not that we typically would do this, but you totally could have chosen, check this out, it's kind of cool. You could have chosen u equal to e to the 6 sine of x. It kind of works. Well, does it kind of work? Let's check. My du, what's the derivative of e to the stuff? So if I take dx equal to du divided by all of that, e to the 6 sine of x times 6 cosine of x, and I replace my integral for e to the 6 sine of x times cosine of x times du over all of this, everything cancels except for the 6 down there. So you're left with the integral of 4/6 du. It's kind of neat. Totally works. I wouldn't do it that way. But you might see something different when you're doing a u-sub. You may think, oh, well, I'm going to try this. Usually it's a better idea to try the simpler thing, but sometimes integrating this is really easy. That's going to be 4/6 u, which is 4/6 e to the 6 sine of x. So you do get back to the same place, and then you would plug in, I didn't change the limits of integration because I didn't want to, and then you would plug in pi over 2 and pi, and you get the same exact answer that we got here. Kind of cool, kind of weird. Yeah. Okay. Let's go ahead and start the journey towards integration by parts. Integration by parts is something you're definitely going to need to know. You're going to learn it for sure. And it's cool. So integration by parts, which we often abbreviate as IBP. Integration by parts. Also known as IBP. Integration by parts comes from the product rule. It's not exactly analogous, but I would say the following statement. The u-substitution is kind of like you're undoing the chain rule. Right? Because with u-substitution, you're kind of looking for the inside piece whose derivative you also multiply by. And the chain rule is you take the derivative of the stuff and you multiply by the derivative of the inside. So kind of like how u-substitution is undoing the chain rule, we're going to see the integration by parts is kind of like undoing the product rule. It's kind of neat. So let's talk about the product rule. So I'm going to use, instead of using F's and G's, I'm going to use U's and V's. But let's write it both ways. So we know the derivative of F times G is F prime times G plus F times G prime. Or using a more standard notation, which is slightly unfortunate because we're using U's and V's, which if you're not careful could look the same. So the derivative of U times V is equal to, instead of writing U prime, I'm going to write du to mean the derivative of U times V plus U times the derivative of V. Cool. And now what we're going to do is we're going to integrate both sides. So we're going to take the integral of the derivative of U times V, and we're going to say that's equal to the integral of, instead of writing du times V, I'm going to write V times du plus the integral of U times dV. Okay, let me ask you all a question. If I took a function and found its derivative, and then found that function's antiderivative, where would I be? Where would I end up? Back where I started. Except you could say, but James, you might be off by a constant. I'd be like, okay, fine, I could be off by a constant, but no big deal. So right, when you differentiate and then anti-differentiate, you get back to where you started. So the integral of the derivative of U times V is just U times V. This part here is just U times V. And it's equal to the integral of V du plus the integral of U dV. And then what we're going to do is we're going to isolate, if you remember which one we isolate, it doesn't really matter, but it does matter. We're going to isolate this one. So we're going to say that the integral of U times dV is equal to U times V minus the integral of V times du. And this is the whole idea behind integration by parts. So so I really haven't said anything yet. Like, I feel like I've just like written a bunch of symbols. You're like, okay, James, sure. So integration by parts, the whole idea is you take the integral of U times dV, and you're going to write it as U times V minus the integral of V times du. Now, here's the idea behind what we're going to be doing. The whole point of this is that what this integral is going to look like here is going to be hard. The integral of U times V dV is going to be hard to do. But the point is that if we pick U and dV the correct way, and then rewrite it like this, U times V will just be whatever, it doesn't matter. And the integral of V times du should be easier to do. So that's the whole kind of point, is that you're going to end up you're not actually finding the integral when you do integration by parts, you're rewriting the integral as something minus another integral, and then that new integral you're subtracting is an easier integral to calculate. Let's see what we mean by this. Yeah, I love that one. So let's look at something like, I'm trying to write numbers to keep things in a more typical process. Let's say we want to find the integral of, sure, let's say x times cosine of x dx. So when you're thinking integration by parts, and after this example, we'll talk about when we think integration by parts versus when we think u-substitution. If I'm thinking integration by parts, I'm trying to make a choice for u and a choice for dv, meaning I'm going to look at this integral and part of it's going to be u. And typically we're going to pick u in a way so that its derivative is simpler. I know that's not a super straightforward piece of criteria, but just go with it for a second. So we're going to pick u so its derivative is simpler. And you're going to pick dv so that this antiderivative doesn't suck. Hopefully it's simpler, or at least not more complicated. So looking at these choices here, if I pick dv equal to x, which we're not going to do, but I'm saying if we did, the antiderivative of x would be more complicated. It would be x squared over 2. If the power is getting bigger, it's more complicated. I mean, it's really not that more complicated, but like, okay, it's more complex. On the other hand, if I pick u equal to x, the derivative of x is just 1, and that got simpler, so that's a good choice. On the other hand, if I pick dv equal to cosine, the antiderivative of cosine is sine, which is really not more complicated. Sine and cosine essentially the same function. They're just shifted from each other. They're not more complicated than one another. Also of note, if you pick u equal to cosine, its derivative would also be something like sine. It'd be negative sine. Okay, but what? So we're going to make the choice that u is equal to x. And really, the honest truth is, once you've picked what your u is going to be, dv is everything else. So after you've got u, dv has to be the entire rest of the story, including the dx. The d something should always equal something with a d something. And then we're going to find all the other things we need. So I'm going to need, let's see, I'm going to need du, and I'm going to need v. So to find du, we're just going to differentiate like we usually would in a u-substitution, although it's not a u-substitution, but we're still going to find du in the usual way. Also, I want to point out, this example totally violates something that we wouldn't do for a u-sub, right? For a u-sub, you would never let u equal x, because that would just be rearranging the whole thing, writing it with u's instead of x's. For an integration by parts problem, totally fine to let u equal x. Happens all the time. And then over here, instead of differentiating, we're going to anti-differentiate to find what v is. So the antiderivative of cosine is sine, not negative sine, right? The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. So yeah, just to be super careful here. We are differentiating here, and we are anti-differentiating here. And that's always the case. And the notation is supposed to elicit that, right? When you go from u to du, you're taking the derivative of u to get du. When you go from dv to v, you're anti-differentiating, right? Because the derivative of v is dv, the antiderivative of dv is v.
So the dx just disappears.
Yes, yeah, exactly. Yeah, the dx just kind of goes away because we kind of did the antiderivative. What we really could write, although we shouldn't, is you could be writing something like the integral of dv equals the integral of cosine x dx, and then the integral of dv is v, and the integral of cosine x dx is sine x. That's all the stuff we're not writing because we don't want to. Cool? Cool. So then we're going to take our integral of x cosine of x dx, noting that our x is u, and our cosine x dx is dv, although we don't have to. And then we're just going to write down what it's equal to using this formula, this integration by parts formula. It's equal to the ultraviolet super voodoo. That's something someone said a long time ago to me and has always stuck. So ultraviolet for UV, right? Like UV rays, ultraviolet rays, minus the integral of voodoo, minus the super voodoo, VDU, voodoo. Can't forget it, maybe. Ultraviolet super voodoo. So we're going to get our U times our V minus the integral of our V times our du. Notice we're not actually writing any U's or V's. We are writing all the things that the U's and the V's and the du's and the dv's are equal to in terms of our variable x, typically. But now look, this new thing on the right is something that is easy to deal with. We know what the antiderivative of sine x is. It's negative cosine x. We didn't know what the antiderivative of x cosine x was. That's something we couldn't have done with just straightforward doing it. So then this is going to equal x times sine of x minus the integral of sine of x is negative cosine of x plus c. And then finally, I would write this as x times sine of x plus cosine of x plus c. Couple notes here. You're going to see a lot of sines and cosines in these integration by parts problems. Make sure you've got the SIGNS's correct. Make sure you got the signs right. The derivative of sine is cosine. The antiderivative of sine is negative sine. The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. So for sine and cosine, their derivatives and antiderivatives always switch their positive and negativeness. So if you know the derivatives of sine and cosine, then you know the antiderivatives are just the opposite SIG and S. I hate the sine and sine sound the same. It's terrible. Anyway, that's life. So one more thing about this one. Let's check to make sure it's right. You can always check to see if an antiderivative is right by taking its derivative. So let's see. If we take the derivative of x sine of x plus cosine of x, you don't really need to write the plus c because we know the derivative of plus c is going to be 0, but let's write it anyway. I'm going to use the product rule here. So I'm going to get a 1 times sine of x plus an x times the derivative of sine is cosine plus the derivative of cosine is negative sine plus 0. And oh, look, I've got sine minus sine. Those cancel out. And I'm left with exactly x times cosine of x, as I should be. Cool. It works. So that is an example of how integration by parts works. You have to pick what u is. Which always sounds wrong when I say it, because I feel like I'm saying you got to pick what u is, but not right. With the letter u is equal to. And then dv is everything else. And we rewrite the integral so that it's hopefully easier to integrate. Questions so far? Oops. Okay. Okay, so how to know when you should be using u sub versus integration by parts. It's not always 100% clear. I'm going to tell you. Sometimes you're going to try one thing, it's not going to work. You're going to try the other thing. But the idea is kind of summed up best in the following. Yeah. So let's look at the difference between these two examples. Let's say I have the integral of, sure, x e to the x squared dx versus the integral of x e to the 2x dx. So this really is where the idea of does one piece look like the derivative of another piece come into play? Because you're essentially, if that's the case, you're looking at the chain rule kind of thing, you're looking at a u sub kind of thing. Because you're basically seeing the derivative of the inside part you took when you did the chain rule. Or you're not going to see that. So what I would say is that this first example is an example of where a u sub is the right way to go. Because if we pick u equal to x squared, our du is 2x dx. And then we can do it, yeah, this is, so du divided by 2x is equal to dx. And then we can rewrite our integral as the integral of x e to the u times du over 2x, and then the x is canceled. So we're left with 1/2 the integral of e to the u, which is 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. Moderately straightforward u substitution problem. On the other hand, over here, a u sub is not going to get us where we want to be. There's not a lot of good choices for a u sub here. You might try letting u equal 2x, right? Because it's stuck inside the exponent, which is the usual kind of way we pick u. But if you do that, you're still going to be left with the same sort of terrible integration by parts problem. If you pick u equal, let's see, let me just point out, if you pick u equal to 2x, your du would be 2 dx, 1/2 du equals dx. So this integral will just become the integral of, let's see, my dx is 1/2 du. My e to the 2x is e to the u. And oh, I've got a leftover x, so I have to do a back substitution. So doing a back substitution where x is equal to u divided by 2, I'm going to get a u over 2 here. This is pretty much the same integral. If I factor out the 2 1/2s, I get 1/2 times 1/2, and I'm left with u e to the u du, which essentially is the same problem. I still have my variable times e to my variable. This is not the way to go. How do I say this the right way? typically you're looking for the difference between here I see like the derivative, whereas here I just see functions multiplied together. So broadly, here's kind of the idea. If you've got some functions multiplied together, you should first look to see if a u sub makes sense. Look for the easy u sub, not the terrible back u sub stuff that we've just been doing. You're looking for an easy, okay, if I make u equal to this, is this derivative there? Great, bang, bang, I'm done. On the other hand, if your u sub is looking like it's not going to be easy, like you might have to do a back substitution, it's probably not the way to go. Oh, there's one word I forgot to mention here. Sorry, let me back up a tiny bit. Typically, you're looking for these differences if you have what we like to call a mixture of functions, meaning you've got things like an x to a power times a trig function, or an x to a power times an e to the something, or an e to the something times a trig function, or an x to a power times a natural log of x. If you've got mixtures of those kinds of things, then it's probably either going to be u sub or integration by parts. And our job is to first check to make sure it's not an easy integration by parts, and then to try and, sorry, not an easy u sub, apologies, and then to try an integration by parts. So here, we would try integration by parts. We're going to let u equal x. And we're going to let dv equal the rest. I would encourage you all to get in the habit of saying just the rest for dv. You pick your u. We'll talk about how to pick u in just a second. And then dv is the rest. Awesome. So here, my du is 1 times dx. And my v, the antiderivative of e to the 2x, not the derivative of e to the 2x. The antiderivative of e to the 2x is e to the 2x divided by 2. This, by the way, is the whole reason we spent time talking about those mini u substitutions way back in the day, because you're going to be doing a lot of integrating e to the 2x, and I don't want you to have to do a u sub for that. We can know that the integral of e to the something times x is e to the something times x divided by that coefficient of x. Totally works. So then we can rewrite our integral as, instead of x e to the 2x dx, it's going to be the ultraviolet super voodoo. So it's u times v, so x times 1/2 e to the 2x minus the integral of v du, 1/2 e to the 2x dx. And now the thing that we are left to have to integrate is a straightforward integral. So this is going to equal, simplifying it just a little bit, x e to the 2x over 2 minus 1/2 times the integral of e to the 2x. We literally just did the integral of e to the 2x, so we can certainly do it again and get x e to the 2x over 2 minus 1/2 times e to the 2x over 2 plus c, which I suppose you would write as e to the 2x over 4, but I've run out of room, so I'm not going to. Questions so far? Okay. Let's do one more example, and then we'll talk about how you pick your u. And it is really how about you pick your u, and then dv is kind of just the rest. So let's say I want to do the integral of x to the 5th times natural log of x. And I'm going to check, even though I know it's not going to work, can I do a u sub here? Not really. You could try picking u equal to the natural log of x. So does a u sub work? If I let u equal the natural log of x, my du is 1 over x dx. I suppose, so doing it the way your teacher typically does it, I suppose if I was trying to actually make this work, I would isolate dx as x times du, and then I would try and rewrite this as the integral of x to the 5th times my natural log of x, which is u, times my dx, which is x du. Well, that seems sucky. You could really make this work if you wanted to by doing a back substitute, but so if you get to the place where you're doing a back sub with something weird, it means you should probably stop. I will point out that if you did the back sub here and you said e to the u was equal to e to the natural log of x, then this would become the integral of x to the 6th times u times du, which would be the integral of e to the u to the 6th times u times du, which is the integral of e to the 6th u times du, which is almost virtually the same as the problem we just did. It's really just like that. Which would mean you'd have to use integration by parts, which means you shouldn't do it this way. This is definitely not the way to go. The big no from me. So instead, we're going to try integration by parts. And again, I'm seeing that we're doing one of these two things because we have a mixture of functions. I have x to a power times a logarithmic function. And I already tried to use them. I'm done with that. So now I'm going to try integration by parts. And usually, no, that's not even a good thing. No. I would say I see less of a function in a function here, right? I don't really see a thing stuck inside another thing here. That's why I'm kind of thinking more towards integration by parts. So what's the better choice for you? X to the fifth or the natural log of x? It's not a good question. Let me ask you a different question. What's the worst choice for dv? Which thing is harder to integrate? Definitely ln of x. We don't even know how to integrate natural log of x. In fact, we're going to learn how to integrate natural log of x using integration by parts. But we don't know how to integrate that yet. So it is almost 100% always the wrong choice to pick dv equal to the natural log of x. And it's almost always 100% the right choice to pick u equal to the natural log of x. Because things are going to get simpler, right? The derivative of the natural log of x is just 1 over x, which is a much simpler animal, right? It's the power of x. That's not terrible. And then dv is, oh no, just say 2 words. The rest. dv is the rest. Thank you. Awesome. Great. So dv is x to the fifth times dx. Definitely get the dx in there. So then our du, derivative of the natural log of x, is 1 over x dx. And our v, which is the antiderivative of x to the fifth, is x to the sixth divided by 6. Cool. Now we just throw the formula at it. You don't have to rewrite the first integral, but I like to. I take that back a little bit. There are some problems where you actually do need to write the integral because you do some weird thing where like you do integration by parts twice and then you end up with the same integral again, and then you add it back over to the other side and then divide by 2. We'll talk about that later. But sometimes you do need to actually write the integral, so it's good practice. So let's see, I'm going to get u times v, so natural log of x times x to the sixth over 6 minus the integral of v times du. So that's x to the sixth over 6 times 1 over x dx. Okay, so I want to make sure all of you know we can't just integrate this by integrating each part. So I want you all to know it's not going to be x to the 7th over 42 times the natural log of x. The whole point of doing this was to make this simpler, right? Also, you can't integrate a product by integrating each piece and multiplying together, right? We know that. Good. Yeah, okay. So the whole idea here is to simplify this if we can. So we're going to write this as x to the 6th times natural log of x all over 6, just because we usually write the powers of x first. And then this right here is going to be a 1/6 times the integral of x to what brand new power? Yeah. Right, we divided. X to the 6th divided by x is just x to the 5th. So definitely, if you can simplify the integrand of your new integral, you are almost always encouraged to do so, especially when you're doing integration by parts. So then we integrate this. We already know how to do it. We just did it before. So we're going to get 1/6. The integral of x to the 5th is x to the 6th over 6. Let's see. I suppose we could finally write this as x to the 6th natural log of x over 6 minus x to the 6th over 36 plus c. That's how you would do that. I forgot my number up here. Questions about what we've done here so far? Okay. So here's what I want to tell you now. There is a mnemonic device for how we typically pick u. It is not 100% always guaranteed to be effective, but for the most part, especially in 16B, it is virtually almost always effective. So how do you pick u? In integration by parts. So your first choice for u is always a logarithm. If there is a natural log, or actually any log with a base of whatever, but typically it's a natural log. So you first are going to pick u to be a logarithm. If you don't see a logarithm, then the next best choice for you is I like to say any power of x. Or whatever your variable is, but let's just say it's x. Some people also say anything that's algebraic, but it's any power of x is a better way of saying it. Thirdly, if you don't see either of those two things, at that point it actually really doesn't matter, but we usually default to picking a trig thing next. And if you're picking u equal to something that is exponential, meaning e to the x, you're probably not doing an integration by parts. It is almost never the case that if you have an e to the x, you're going to let that be u. It is almost always better for the e to the x thing to be your dp. So that's the usual, and some people will say the acronym is late. It's worse in 21 series because you have to also talk about inverse trig functions, and then it's Lie8, which doesn't sound nearly as good as late. So this is how you pick your u if you think integration by parts is the way to go. So let me show you one more quick example. So this one we won't actually do, but let's say I want to integrate 1 over x times the natural log of x quantity squared. If it was in, so again, I want to point out, if you were thinking integration by parts, whatever you choose for something, the other dv part has to multiply out to the whole, so the whole thing is your integral. So like if we picked u equal to, there's not even a good choice here, because you can't pick natural log of x, you have to pick 1 over natural log of x squared, right? That's kind of like, right, because they have to multiply to the thing. So this is definitely looking more like it's probably a u-substitution kind of problem. And I can see that because I see that if I pick, what thing can I pick u equal to whose derivative is also in this integral? Is its derivative there? What's the natural log of x? Oh, and do I have 1 over x? I do, yeah. So that's a really good choice. This is definitely a u-sub problem, because we see that if we make a good choice for u, our derivative 1 over x is also there. That's like someone like throwing a big sign at you like, hey, do a u substitution. You pick the u and its derivative is there. That is a primo sign that you are doing the right thing. Almost all the time. You can never say anything all the time for this class because like there's always exceptions usually, but almost all the time it's a really good sign. So then if we did this, I do it the dumb way you're doing x du dx, fine. I'm really not a fan in case you hadn't noticed. I'm gonna write this as 1 over x times u squared times x du, and then the x's cancel. I find this annoying, but whatever. Okay. So then it's the integral of u to the -2 du, which is u to the -1 over -1 plus c, which I would certainly write as -1 over u plus c, and then replace the u with what it's equal to, and get -1 over the natural log of x. Something worth pointing out here, it is not the natural log of the absolute value of x. Oh, sorry, good call. It is not the natural log of the absolute value of x. You only specifically get the natural log of the absolute value of x if you have integrated 1 over x. We never did that in this problem, so we shouldn't be just tossing in absolute value for no reason. But people have a common tendency to be like, oh, natural log of x, there should be an absolute value there. Only the case if you integrated 1 over x to get there. All right, that's all we got. I'll see you all on Friday. And if there are still questions about the u-sub, back-sub stuff, come see me in office hours right now, or we can still talk about it on Friday, I guess, because your homework's not due till Friday night. Wasn't it like supposed to be due like on Monday? Yep. Like, no. Okay. Okay. There's only so much time. I know, right? I'm just surprised that, I mean, I understand like wanting to,
on the syllabus.
right. When I understand the teacher like wanting to address students' questions, but typically teachers are very much like, you know, we have to get through the material, so there's only so much they can do in class, and they kind of have a plan already. I mean, it's good, I guess, but also like you also have to get through the material. What happened? Something weird happened. I'm like, oh, hopefully the video is gonna be able to be posted later, and I'm having some Zoom issues, so there might not be a video recording. Fine for all you guys. We'll see. Just quit all of a sudden, which at least it didn't quit until after the class. What's up, Maya?
So I noticed that the roll call attendance, I've like attended every single one.
Uh-huh.
I've watched every single video and filled out the form. every single
Yes, I was just updating it before class, so it might just be that. I would say don't worry about it yet if there's something wrong, because I'm still updating it because the data is all over the place.
Cause it's just,
Worry about it. It'll be fine either way. Also, yeah, I would I'm just trying to get the data right. So if after, give me until the end of the week, and then if something still looks wrong, let me know.
okay. Thank you.
You're welcome. Yeah.